Alright, I think we can start today's webinar now. First of all, a warm welcome to everyone who joined. My name is Niels Verdijck and I will be your host today. Apart from being your host, I'm also a customer support engineer in Diabatix. So that means if you have any questions or if you do a project with us, you'll for sure get in contact with me again. Alright, I think that's a very brief introduction about myself. So we can move on to today's webinar topic, which is, of course, how to benefit from our generative design tool to optimize your test tube warmer. All right. Once you log on to ColdStream, our platform, you'll be presented with all your projects, either ongoing or finished. As you can see, I'm logged on to the demo company account, and we have quite a lot of projects. Of course, when the first time you will log on to the platform, you won't have any project, so you'll have to create one. So you can simply do that by pressing the Add Project button. Give your project a new name, new project, give it a description, and press the Add Project button. Of course, I advise you to give it a better name and a better description. Okay, of course, that's something I don't have to do because I prepared for this webinar, of course, so we can move to the project folder for today's webinar. Once you move to the project folder, you'll be presented with all the cases that are assigned to that project folder. So we currently have only two cases, a finished one and a created one. Once you create a new project, of course, there won't be any cases in there, so you have to create a new one. And you can do that by pressing the Add Case button on the top right corner. Again, you'll have a pop-up window asking for the name, this time for the name of the case, not the project. So let's give it optimization webinar. I really advise you once more to give your cases proper names. This will keep your project folder organized as well. And then we have to select a case type. So we have two options. Either we can select design or simulation. If you press simulation, then we'll let the platform know that you just want to do a calculation or a CFD simulation with your case. So for instance, if you want to know the pressure drop through your design, or if you want to know the temperatures of your heatsink, that's something you can do by using a simulation case. If you press design, then we'll let the platform know that you want to benefit from our generative design tool. So you want to optimize something. Given our name, this is something we want to do. So let's press the design button and then press Add Case. As you can see, we have successfully created the case. So we can start with the setup. You can do that by pressing the Start Setup button on the top right corner. Currently, there are no geometries in there, of course, because it's a newly created case. So we have to upload a step file. We have to navigate to the desired step file, open, and then we can populate the case. So once you press that button, the step file is sent to the platform, and all of the geometries that are present in that step file will be extracted. As you can see, it's quite a large file, so I'll spare you the process of it being extracted and immediately go to the case setup itself. So these are all, or this is what you would see if there are geometries inside the step file. So I uploaded all of them at the same time. And we can start with the case setup itself. So let's go to this one first. So this will be our plastic material holding everything together. So in your test tube warmer, you'll have some interface here with a screen, perhaps, and some buttons to change the temperatures of the desired temperature. Sorry, but of course, yeah, I've left it out to make the geometry as simple as possible. Okay, so this is of course a solid region, so that's why it's selected solid. We can change the name if we want, but I think it's fine. Next, we have to select out of what material it is made. So let's use bakelite, which is of course a thermoplast, which I think it's very appropriate for this case. If you want, you can enable radiation, but let's leave that one out. And you can assign some volumetric heat source to be produced inside that entire region. But of course that doesn't produce any heat, so let's leave that to 0. Alright, next we can move on to this. So this is a surface patch. This is why it has a different symbol compared to our test tube heater. I will come back to these in a minute. So this is our surface patch through which some of the heat is escaping to the environment. So it's an external wall. You can change the name if you like, but let's keep it as is. You have to specify the heat transfer coefficient, 10 being a very standard value for heat transfer to the environment. We have to present, we have to input, the environmental temperature, which is 20 degrees Celsius. Do notice though, the platform expects temperatures to be inputted in Kelvin. So you have to add 273.15 to your desired value in Celsius. Alright, these are some additional parameters which you can include. For instance, the thickness of the external wall and the conductivity, but we won't be using that. And we can ignore these values because these have to do with the radiation, and as you know, we didn't include the radiation effects, so we can ignore those final 3 input parameters. Okay, that's it for the test tube heater for now. Let's move on to the geometry, which is called block heater. So this is the geometry where the test tubes are placed into, which of course also a solid region. Yeah, solid region. You can change the name if you like, but let's keep it as is. And you can select the material. Let's use a good conducting material for now, so aluminum. Again, we can include radiation or have some volumetric heat source. That's not relevant for this case. And again, there is some heat being evacuated to the environment. So the same drill, external wall. Let's change the name of this one, environment. Block heater. The same holds true for this surface patch. So we need to specify the heat transfer coefficient, the environmental temperature, and again we'll ignore any thermal interface between the block heater and the environment. Okay, that's it for this region. Let's move on to our test tubes themselves. I'll hide this one. So our test tubes, fortunately it's a dark purple color, so it's not that visible. But our test tubes are another region, of course. Again, it's a solid region. You can change the name if you like. Now we have to specify out of what material it is made. So it's made out of glass. And we'll ignore radiation and any volumetric heat source. Our test tubes, of course, act as a fin, conducting the heat to the environment. So we have an external wall again, mimicking the effect of heat escaping to the environment. You can change the name again if you like. So it's pretty much the same drill. We'll use the same boundary conditions as for the other environmental representations. And we can ignore any thermal interface between the test tubes and the environment. Lastly, we have the thing we want to cool or to keep warm, rather, which is the test tube fillings. For now, we'll model it as a solid. You can, of course, model it as a fluid. So solid. And let's use water properties as our fillings themselves. And as you can see, there's also an opening to the environment. So let's fill in the last external wall. This will use a lower heat transfer coefficient, because in the test tubes it's much more difficult for the air to conduct the heat, or to convect the heat away from the inner filling. So that's why we lower the value to model that. But let's use the same value for the environmental temperature. Okay, so that's all the relevant information about the different regions. Next we'll move on to the sub-regions. So for every design case, we need to let the platform know, we need to let the platform know what it needs to optimize for, or where it needs to place material, And for this case, we will allow the optimizer to generate wires in 5 different regions. So on this side of the block heater, on the opposite side, at the front, at the back, and below at the bottom. So let's fill in all the relevant information, starting with this one. So it's a design subregion. So this really lets the optimizer know that it can place, or can optimize, or can influence the design, by playing around with what it does in that subregion. You can change the name if you like. Next we have to specify the manufacturing type, which is the electric wire. Select manufacturing settings. Let's use the predefined one, which I defined earlier when I prepared for this webinar, of course. And let's specify the voltage which is present over the wire. And this will impact the amount of heat generated through the wires, together with the material that will be used. So basically, the resistivity parameter which is assigned to this material type. Okay, that's all for this subregion. So let's repeat all of that for the other ones. So again, the design subregion, electric wire manufacturing technique with an RF min of 2 millimeters, meaning that the wire will be at least 2 millimeters thick. Let's use the same voltage and the same material. Let me quickly repeat that for all other ones. So again, electric wire, voltage 220 volts, same manufacturing technique settings, and same material. Second to last one, electric wire, 2 mm wire thickness, 220 volts, and our material, our wire is made out of copper. Last one, design, electric wire, 2 millimeter thickness, 220 volts on the wire, and it's made out of copper. Yes. All right, so all green check marks. That means that the submit button is lit up, so we can submit the case. Unfortunately, we still have to tell the optimizer what to optimize for. So some targets are missing, and that's something you can do on every geometric entity by scrolling all the way to the bottom. Press Add Target, and then specify what objectives or targets you want to optimize for. Okay, so we have a few options for this one. You can use the temperature spread minimization as one option, where you want to optimize for, I forgot what value, let's use 360 kelvins. I'm not too sure what exact values I use, but this is a first option that we can use. So where we want to minimize the spread around 360 degrees. So basically, if you want the test tube fillings or water from earlier to to be kept at a fixed temperature, or to keep it as close as possible to a fixed temperature. This is one of the objectives that can be used. Another objective that can be used is using the temperature variance minimization. So it basically acts very similar to the temperature spread minimization, but you don't have targets. So if you want to use this one, you'll have to specify some other targets as well, mainly a temperature minimum temperature constraint. Let's put that to 358 kelvins. And another one, it's a maximum temperature constraint to, for instance, 361 kelvins. So basically what I did now is, the second option, I gave the optimizer a bit more freedom to minimize the temperature variance, but I kept it between the lower and upper bounds that I specified. If you want to use the temperature spread minimization, sorry, then you let the optimizer know that you need to keep the difference between the target value as minimal as possible. I hope that's clear. If it's not clear, then feel free to let me know in the comments, in the Q&A interface, and I'll get back to it during the Q&A portion of today's webinar. Okay, so we have our target, so we're able to submit our case now. So if we scroll all the way to the top, we can submit our case. Now the case is already being pushed to the platform, so to do some basic validation checks. And I'm pretty sure I won't have any troubles. If you have any troubles, you don't see this pop-up window, but you get a pop-up window with all of the warnings or errors. For instance, if something is missing, for instance, a target or something, or a design subregion, that's something the platform will warn you about. If there are no errors, you'll get the following pop-up window, where you have to make two final choices. So the first choice you have to make is what amount of credits you want to spend on this case. As you can see here on the top, I have 460 credits available to this account. So I can use the maximum of 200 credits to this case. If you don't have that many credits available, you can move the slider, to a lower value. As you can see, our credits have decreased to 75. Basically, the less credits you spend or you assign to this case, the less computational resources are made available, and also the longer your case will take. The next choice we have to make is what resolution level to select. If you select a detailed design, then the resolution of the mesh is very fine, so very detailed, and your design is fully manufacturable. If you specify your case to be of type conceptual, or resolution to be of a conceptual resolution, then the mesh is slightly coarser and the design is not fully manufacturable. This is something to really fine-tune your optimization settings, because as you can see, a conceptual will always finish sooner compared to a detail, which makes sense, of course, because the mesh is it's coarser, and it doesn't have to meet all manufacturability constraints. Okay, so you can press, for instance, you can submit it as a detailed case, and then it's pushed to the platform and it starts running. Of course, we don't have to wait for it to complete, so we can stop calculating button. Yes, I want to confirm that I want to stop it. Be careful though, if you stop your case, all the progress is lost from the platform. So if you stop your case and resubmit it, hoping that it will pick up from where you left off, that won't happen. So all the data is deleted. So you really have to start from scratch again. That's something you have to take in mind, of course. Okay, let me check my notes to see if I forgot something. It looks like I explained everything, so we can move on to post-processing. Yes. So I'll show this. So once your case has finished, it will transition from running to the green finished. You'll also get a notification that your case has finished. So once you press your now finished case, you'll get the following overview. So the first thing you'll see is the case summary file, basically presenting all of the general performance values. So for instance, all of the temperatures of the different geometric entities. You can switch around what units you want to view it in. And as you can see on our block heater, our temperature difference is less than 1 degree. So I would say our optimizer did a very good job keeping the temperatures in check. Of course, no pressures, because there are no fluids. No volumetric flow rates, because there's no fluids, and the heating values. Some other relevant information is, for instance, all of the areas of the different surface patches, any imbalances, if there are any. Alright, next you can plot the results in charts. So basically, the results charts tab will give you the same information as the case summary file, but just in chart format, which makes it a bit easier if you need to create a project, for instance, a report on it. Of course, no data of the pressure once more. The final thing the optimizer allows you to do, or the platform, sorry, allows you to do, is to view the results in 3D. So yeah, once that loads in, you can expand all. You can again play around with the geometry in the UI, and then plot all of the different parameters. So for instance, let's look at our, oh, that's not what I wanted to do, hide or yes. For instance, we want to look at the temperature distribution in our block heater, and as you could expect, the temperatures in the middle of the block heater are the lowest, because as you remember, our heat sources were at the sides and at the bottom, and our test tubes really acted as fins conducting the heat away to the environment. So it's no surprise that that the temperature is the lowest here in the middle. And we can also have a look at our optimized design, so our wires. So let's plot them all. So each subregion will have its own results in the case summary results tab, which makes sense, of course. And then you can overlay the temperatures, for instance on the right here, or I have to zoom in a bit more to make it a bit more clear. Yes, and as you can see, the results are pretty much as expected. So a low density of the wire at the bottom. So for instance, there's hardly any wire here in the top left bottom, and a much more dense wire at the top. Similarly, if we go to the bottom one, so let's plot the temperature once more to make it a bit more visible. And let's do something like this. Yes. So now we have a perpendicular view to the bottom wire, and as you can expect, at the edges, especially here at the shorter edges, the density of the wire is much shorter, because the heat is partly generated here by the wires at the side, and it's much more dense here in the middle, which makes, of course, perfect sense. Okay, I think that's all the post-processing that's required, or that I wanted to show at least for this webinar. If you want to do some more custom post-processing, you can always download the results. So by pressing this button, a zip file with all of the VTK data will be downloaded into your downloads folder, and you can, for instance, open that in ParaView if you want to have some clips or something, or some slices inside any of the regions. That's something you can do by pressing the download results button. For every design, there's also a download design button. Again, if you press that, a zip file will be downloaded into your downloads folder, but this zip file will contain all of the step files of the different design regions. So we had 5 design regions. So our zip file will contain 5 step files for each of the 5 design subregions. Okay, I think that's all for me. Yeah, I think we can move on to the Q&A portion, starting with our first question. Why did we use a solid region as our fillings and not a fluid region? Which is a very good question. And let me go back to the setup of our case. Let's do our test tube fillings. So as you remember, I modeled them as solids. We can of course model them as fluids by pressing the Add Fluid button. I will have to select a fluid material now. Let's use water again. Let's fix the properties at that temperature. But now we'll have to use buoyancy, because otherwise the equations won't be able to, the governing equations won't be able to converge. So that's something we have to use now. But buoyancy has the pleasant surprise of being very tricky to solve. So meaning that if you submit your case for each fluid region which has buoyancy, the time estimation will double. So it's quite expensive to run buoyancy cases. You'll also have to input the reference pressure, being the absolute pressure. So let's use atmospheric conditions. So 1 atmosphere and 20 degrees Celsius. And have a gravitational vector in the -y direction. As you can see here, the yellow arrow represents the y-axis, and it makes sense that our gravitational vector is pointing in the negative y direction. So yeah, basically because the time estimation will increase dramatically if you use buoyancy, it's easier to just model it as a solid region. So that's just why I did it. You can of course use a fluid region with buoyancy, but expect the time to completion, the estimation to increase quite dramatically. I hope that that explains the answer very well. So we can move on to the next question. Could you explain the targets? Yeah, okay, so the targets are not clear. Let me move myself as well. Yes. So as you remember, we had our targets put on our block heater. And we used a temperature variance minimization with a minimum and maximum temperature constraints. So what the temperature variance minimization does is it minimizes the temperature variance. So basically, it tries to minimize the maximum and minimum temperature of that entire region. And of course, our fillings will need to be kept at the desired temperature. So that's why we have to impose these temperature constraints as well, because otherwise the optimizer doesn't have any real reference to what temperature it needs to minimize for, and most likely it will just try to increase the temperatures to infinity, because at infinite temperature everything is uniform. So that's why you have to impose those constraints. The other option was to use a temperature spread minimization, this one. And then we have a target value. So let's use 360.15 Kelvin, which basically acts in a very similar way to the temperature variance minimization. But now we have a target. So now the optimizer cannot increase the temperature to infinity, but it has to try to heat up the different regions of the block heater to within or as close as possible to this target value. So that's why we have that's a subtle difference, sorry, between the two options. I hope it's very clear. If not, yeah, feel free to let me know in the Q&A pop-up window. Let me quickly look at time. I think we run out of time, unfortunately. Don't worry, all other questions will be answered by email, so you'll hear back from me once I've answered them. Okay, I want to thank you all for your attention. Feel free to try the platform yourself, as you can basically quickly. You can quickly ask. You can quickly request access. To the platform by going to our website and pressing the request access button. If something of the case setup itself is unclear, you can always go to our documentation page, where we have explained everything pretty clearly, I hope. So for instance, for our targets themselves, you can go to the design chapter and go to targets, where the temperature variance minimization and temperature spread minimization are explained in more details. You can also watch our previous webinars or contact support. So yeah, basically go to the links and you can use whatever, you can create a support ticket, whatever your needs are. Okay, that's it for me. I wish you all a very pleasant day and hope to see you soon. Okay, take care. Bye.